Hi, and welcome. Thanks for joining us in this session. My name is Javier, and for the next 30 minutes or so, we will be talking about the different trade-offs that you can encounter when you want to use different types of CNS devices and how these trade-offs maps to different use cases. So let me share my screen. The first question that we get when talking about CNS is, why do we even need a new interface in NVMe? NVMe SSDs are already mainstream. They offer great performance. They're easy to deploy. They scale very well through NVMe over fabrics. However, we still have a number of challenges that we have not been able to tackle through block-based conventional NVMe solid-state drives. The first one is reducing the cost gap with nearline hard drives. The second one is reducing the write amplification factor and the over-provisioning, which are so tightly coupled with the way we design block-based flash translation layers today. And the third one is how we provide an explicit mechanism to offer quality of service in multi-tenant environments. So we will address these challenges. And first of all, we will talk about the basic concepts of the zone namespace specification and the benefits. Then we will cover the three main use cases that we see for zone namespaces. And then we will dive directly into the core of the talk, that is the trade-offs when designing a host-based CNS host FTO. I will have a couple of back slides, which I will not cover here, but they will be available in the slide deck. So I hope that will help you. If there's something that you don't understand, please check those slides at the end of the talk. So in terms of CNS benefits, there are three main categories that we identify. The first one is that CNS allows us to reduce write amplification and over-provisioning. We can do this because by using zones, we can directly map data structures in the host objects to these zones and remove a number of redundancies in terms of mapping tables, in terms of ways of doing data movement, which trigger that we do not need to move data in different layers, and we do not need to save a portion of the NAND to maintain the performance while we do that data movement. The second benefit is in terms of quality of service. So we will see how there are different zone configurations that would allow us to enforce a strict QoS. And I hope that by the end of this talk, you understand this and you know which trade-offs you need to take if you want to enable quality of service through CNS. The third main benefit is the total cost of ownership, reducing it. And it's kind of a consequence of many things. So first of all, by reducing write amplification and over-provisioning, we are extending the lifetime of the SSD. That's money. When we are enabling higher bit count cells like QLC, that's money. When we are reducing the number of mapping table, the size of the mapping table, and probably the number of the mapping tables on the device, because we're working at a zone granularity instead of working at an LDA granularity, we can reduce the DRAM on the SSD, and that is money. So let's go directly into the basic of the CNS NVMe command set. Now, there are many talks out there, also within the virtual FMS, that you probably want to see before this one if you're not familiar with CNS. I will give an overview, but I will not get into the details. So I'll refer you to those talks before we continue here. There are three things that you need to understand when you want to get a grasp on how CNS works and how you map that operation to the benefits. So the first one is that the LBA address space is divided in zones. That's pretty obvious. This zone will become our mapping unit. And this is important because that's how we're going to reset, how we're going to manage the SSD on the host. The second concept is that of the write pointer. Each zone has a write pointer associated with it. Whenever we write to the zone, we have to do it sequentially following the write pointer. Now, there are two ways we can write to zone devices. The first one is through the write command, normal write command. When we do that, we have the constraint that we have to do it at QDepth1. This is because NVMe does not guarantee ordering, meaning that even though we write sequentially to the device, even on the same NVMe queue, if we have several IOs in flight, there's no guarantee ordering when they arrive to the device, so we might violate the write pointer. So when we're using writes, QDepth1. There's a different way of writing to a zone device, and that is through the append command, which is essentially a way of sending a nameless write to a particular zone in such a way that we do not specify the specific LBA in the zone, but rather we let the device choose that LBA and returning it to us in the completion path. This has its benefits, and it also has its challenges, and we will cover that in a couple of slides. But for now, bear with me. We have the concept of the write pointer. That's important to understand. And whether we use the write command or the append command, we need to consider that the write pointer is there. The third thing to understand is that each zone has a zone state machine associated with it. And that zone state machine, its transitions are primarily driven by the host. Now, I do not have time to get into the details of each state and each transition. I will focus in what for me is the most important transition of all, and that is the transition that allows us to put a zone back into the empty state. That's when we reset the zone. And this is because this transition is the one that is allowing us to do host garbage collection, which is the one that allows us to reduce write amplification, reduce over-provisioning, and virtually eliminate data movement within the SSD, causing latencies, unpredictability in general. The spec is available in the NVMe Express website. It's publicly available, so please download it and take a look at it. There is a couple of extensions that are very interesting for CNS. One is a simple copy, which is already ratified and publicly released. The other one is some random write area, which we're still discussing in NVMe. If you are part of NVMe, I challenge you to go and be part of the discussion and try to make the some random write area DB better. I will not be covering it in this talk due to time constraints. I want to focus in other things, but I do have one slide at the back that you can take a look at to get the concepts of the some random write area and why it is of importance to the CNS overall NVMe ecosystem. So now, in terms of use cases, we see three main use cases, again, that can take advantage of CNS. The first one is, I think, the most obvious, and that is the use case of archival. This is because it's very much related to cold data and can already leverage the zone ecosystem around SMR hard drives. Zones in this use case are very large. They prefer to data that is very cold, very immutable, and they require large queue depths to be able to saturate demand. I will talk about this specifically in one of the trade-offs, so let's park it there. The second use case is what we're calling log IO. As you're very well aware of, we have a number of applications and file systems that are designed to be flash friendly. This essentially means that they try to be append only, use log structure, data structures as much as possible. For this use case, these applications and file systems are the ones that are going to be able to adopt CNS easiest and really shine on the benefits they want to offer, because they are going to be able to complement it with even less write amplification, even less necessary over provisioning, better semantics to do host-based garbage collection. This is for general storage systems. So the ones using these paradigms of log-structured file systems or databases will be able to use CNS and take advantage of it very, very quickly. Here zones, they will be able to be large zones, smaller zones. Again, I will touch on that in a couple of slides. The third use case, which is probably the less obvious, is that of IO predictability. And here we rely on a particular way of organizing zones in the device. If we choose to do smaller zones mapped to a particular number of physical resources, we will be able to have several applications within the same SSD and still be able to provide IO predictability across these applications. So in essence, we can explicitly address the noisy neighbor problem with zones if zones are mapped in the right way. Again, I will touch on this when we cover the trade-off on how we map zones on the device. But I wanted to give you an overview of these three main use cases which can be covered with zones. We just need a little bit more of work to do. So now the core of the talk is, if you want to adopt CNS and you want to write a CNS host FTL, what is your design space? We're going to cover what are the options you have in terms of mapping zones so that you can decide different CNS devices and different ways of doing things. What is the right models that you can use for different applications? And then what is the IO submission model that you can choose? Now, this is going to be interesting because this is a never-ending trade-off that you need to take, but we're going to speak to why it is especially interesting when we talk about CNS. So, zone mapping, coming back to the use case, if you want to map it, archival is very much large zones. Log IO is in the middle between large zones and small zones. IO predictability goes more to the small zones. So when you go through large zones, these are zones that either span across the whole NAND array on the device or through a large number of dies on the CNS device. This is very good for systems that are already deploying SMR hard drives, because the changes to the host ecosystem are minimal. You can adopt this very easily by doing the small changes at the driver level. If you use Linux, these are already available in mainland. These also have the benefit that since you have a single zone that you need to take care of, you do not need to think about striping. You do not need to think about how you're going to map to the zones on the host device, at least for a single SSD. There's a couple of drawbacks when you use large zones. The first one is that you do not have visibility of the parallelism of the device. And this might be okay especially for archival, this might be okay. The second problem is that you will have to deal with very large zones, especially if you use the CNS in combination with QLC. Now, this might become a problem because when you have large zones that can be several gigabytes and you do host garbage collection, you're going to introduce write amplification, yes, unless you have very large objects that are mapped here. And this is kind of counterintuitive, and we do see people having trouble with this. The third drawback is that if your CNS SSD, if you want redundancy, RAID, for example, large zones are basically going to put that redundancy into the SSD. So you're stuck with a particular type of redundancy, and you have to stick to the over-provisioning that is needed to cover that redundancy. So you don't have that flexibility on the host side. On the other end of the design space, you have small zones. Small zones are good if you want to control data placement and quality of service by using this LBA separation. So that if you have a way of knowing where your zones are mapped, you can play with it to either assign it to different applications or assign it to different parts of your application, your user IO threads and your garbage collection threads. There's also the benefit that if you want to do system-based redundancy, you do not need to pay for the extra over provisioning that is needed to do also redundancy on the device. So with the smaller zones, we can get rid of that device rate. The third benefit is that at a system level, if you're using several SSDs and you're striping across those SSDs to get the bandwidth that you require, you are already doing striping, you already have that logic, and you already have accounted for the CPU utilization. We are just changing the granularity from a single namespace block device to zones. So that extra work is not needed. Now, the counter argument for this is that if you're using a single SSD, the drawback of using the small zones is that you will have to pay for the logic of doing the striping, and you will have to pay for the CPU cycles of doing the striping. So this is something you might want to think about. The other drawback of this solution is that currently we do not have a standard way of representing these memory units or isolation domains in the CNS spec. From our perspective, we see small zones a better fit for the use cases we're hearing about CNS. Gives the flexibility that allows people to create a hierarchy of CNS devices and target different use cases, including archival, without having to buy dedicated devices for dedicated parts of the system. We obviously need to do more work on this, specifically into how we bring this to the standards body. So stay tuned. The second trade-off is in terms of the write model. Now, we described before, when you write to a CNS device, you can use write at Q depth 1. Now, this is very limited. We have heard of use cases where this is okay, because the overall system is using a layer of persistent caching, system memory, NVDIMMs that allow to to provide the performance to the user and then have some sort of write back where performance is not important at the CNS layer level. This is probably a very specific use case, not for everybody, but I wanted to mention it here that it is possible to do it this way. If you're using large zones, append is the way to go. This trade-off is basically, you have these large zones because you want to simplify part of your host stack, especially for a single SSD, but you don't want to lack the performance. You can use the append command and increase your queue depth. The only challenge is that you will have to do changes to your completion path to remap the LBA that on the submission is now anonymous and on the completion is real. There are some file systems or applications where this is fairly trivial or easy to implement. There are some other cases where this is more complicated. It is up to you to decide in which end you end. The third way of writing is zone striping. So now, if you're using smaller zones, you have the possibility to manage your bandwidth latency trade-off by selecting to which number of zones you are writing based on the bandwidth that you need on that moment, or based on the number of applications you want to run on a single SSD at the moment. As I mentioned before, we do not have a way to get this standardized yet, or it's not on the standard yet. If you decide to go this way, we do like this model. We think that it addresses some of the real issues, especially to provide the smaller zones. Talk to us. There is as I mentioned before, it has benefits in terms of providing QoS. But if you're thinking of a single SSD level, you will have to deal with striping, which might be a cumbersome if you don't already do striping across several devices. The third trade-off is how do you submit I/O, and I think this is a never-ending trade-off. Some people prefer to use in-kernel I/O. We have better and better I/O paths, lately I/O urine. So where you can match performance of SPDK on the kernel path. You can also choose to use an NVMe driver in user space and use an SPDK. I'm not going to get into which one is better. I think everybody knows that the benefits and the drawbacks of each solution. What's interesting here is that when you ask people to rewrite their applications, and we know that from the open channel times, it's not that good a reaction. And even when you get away of CNS and you just think of block I/O, rewriting an application to, for example, today use I/O urine, you really need to argue for that within your organization. For CNS, you already need to rewrite part of the application, and CNS being part of NVMe makes a good argument for it. So I can see that many people will be presented with this decision. And it's not always easy to say, I want to go with one or the other, or I want to do a POC here and see what the differences are. To tackle this problem, we are providing something that we call XMBME. Now, XMBME is a library that presents a common I/O API for what we call NVMe native applications. That is, applications that do think about latencies, do think about bandwidth, and today do think about CNS. The value proposition is when you need to redesign your application, you need to choose an I/O backend. We give you the possibility to not making that decision. So we provide a common API where you can choose at runtime, actually, through which I/O backend you want to submit the I/O. So your application, without changes, if it aligns with the XMBME API, will be able to submit through I/O urine or through SPDK without changes. It would actually be able to run if you, for example, use SPDK or on either Linux or FreeBSD. And you will also be able to run it on Windows. I would like to point you, I don't have time to get into the specific details of XMBME. I want to mention that we've done extensive evaluation. We have come to the conclusion that the cost is around 15 nanoseconds. That is around a memory access. And we can match the I/O backend performance that you can see both in I/O urine and SPDK of these 10 million IOPS per one thread. I would encourage you to go to GitHub and get the latest version of XMBME and take a look at it. And go to xmbme.io where you have a number of talks from Simon. The latest one, I believe it is in SDC USA, where he go into the specifics of XMBME, how to use it, what's the state, how you can get involved and contribute to it. So, look forward to your contributions to XMBME. Now, we've gone through the basic concepts of CNS, the use cases, archival, existing log I/O applications, I/O predictability. We've gone through the different trade-offs on how to design a CNS host-based FTL, from which kind of zone representation you need, large zone, small zones, with the way you need to write to the device, and the latest part, how you actually submit the I/O, which I/O backend you use, and how XMBME can help you. Now we put it all together in this RocksDB case study. We have done our own port of RocksDB based on XMBME. And here we make use of, we choose small zones because we prefer, applications like RocksDB use level trees. So it's not always very large objects. SS tables, in the beginning, you might have fairly small SS tables. Having very large zones will create a lot of write amplification when we need to garbage collect those zones and do the compression and the compaction for them. We have chose to use striping across these zones. We actually also use the sum random write area because there are, even though SS tables in RocksDB are fully sequential, there are configurations where you can spare some of the write amplification by doing in-place updates at the end of the SS table for the metadata. So we take advantage of the sum random write area to do that. Now, I know I have not touched on that. Please go look at the back slides or at other talks like the one in SDC this year to fully understand how the sum random write area works. Putting it all together, we see that we can get a write amplification, we can improve the write amplification when using the CNS backend through XMBME. We see a write amplification of around 1, is 1 and then 5, 6 zeros. This is actually because we have not gone and done the work on the LSM tree to perfectly map the SS tables to zones. You can improve that, but realistically, you will always have some level of lost LBAs at that level. But the interesting part is that when we run the same workload of RocksDB in this backend, or in a backend that uses a file system that uses CNS, or when we use a backend that uses a file system without CNS, we see that at a software level, we can have a 2x reduction on write amplification. Now, this tells a lot about how these redundant mappings can influence the write amplification. And we're not even talking about the device write amplification in itself. So this is only at the software level. The interesting part is that if you know the write amplification on your device, at any moment in time, the write amplification on the host is a factor. It factorizes the write amplification on the device. So that number can be pretty large. I do not want to give you an absolute number of the write amplification because that would be choosing, I can find workloads where I can tell you 20x improving write amplification, but that would not be true. Depends very much on how the workload depends very much on the write amplification, the vendor that you use today, how you use the device. So I would rather leave it to yourself to take this 2x reduction on write amplification at the host level, which can be measurable and reproduced by anybody, and then use that to factor and multiply by the write amplification that you have on your device, and the benefits you see can come from that. So I think that takes all the time that we have. Some conclusion points: 3 main benefits of CNS: reduce write amplification and over provisioning, better QoS, explicit mechanisms to provide QoS, and reduce total cost of ownership. CNS has a lot of use cases. It's not only meant for archival, it can also be used to provide IO determinism, and it can also be used to amplify the benefits of Flash-friendly databases, applications, file systems today. And we are actively working in extending CNS to facilitate the transition of open channel SSD users to CNS so that they can leverage all the benefits of NVMe. We have covered different trade-offs on how to design a zone FTL. You can choose one another. It depends very much on your application. It depends very much on the work that you've done previously and the work you want to put into it. And it also depends on the different types of SSDs you're choosing. Either from, same vendors will have different types of SSDs, and across vendors we have different types of CNS SSDs. And we have presented you with XMBME, which we believe we see from early adopters of CNS that is becoming a fundamental part of how to design the transition and the rewrite of applications for CNS. And there is actually a very solid ecosystem in Linux with a lot of vendors contributing. Kudos to Western Digital, who has done an amazing job from the early times of the zone device abstraction in Linux to the adoption of CNS today. I also have a slide on the backup where you can see the overview of the whole ecosystem from different tools, NVMe CLI, block zone, plugins for FIO, the old kernel architecture, QEMU, etc. So again, awesome that we have such a good ecosystem and that people is starting to contribute actively to it. And then finally, a call for action. If you're interested in CNS, you see that some of the use cases we talk about, some of the things that we're saying in terms of the trade-offs resonate on you, please reach out to us and we'll be happy to talk about it. So thank you very much for your time. I hope you enjoy the virtual Flash Memory Summit. It is a pity not to be there and be able to go grab a beer with you guys, but please reach out and we can always do a virtual beer, which is like super popular nowadays. So thanks a lot and enjoy.